By 2026, some of the most ambitious and expensive mega projects in US history will finally be finished. From game-changing stadiums to the replacement of gigantic bridges, these builds have been decades in the making. In this video, we'll reveal the scale and impact of America's biggest mega projects that will be completed by 2026. In the midst of a sweeping modernization effort to upgrade the vital Northeast Corridor rail line, the Portal North Bridge Replacement Project in New Jersey stands out as a transformative undertaking that directly addresses one of the most notorious infrastructure bottlenecks in the region. Originally constructed in 1910, the existing Portal Bridge was a swing-span design that rotated horizontally to allow marine traffic to pass on the Hackensack River. This outdated mechanism frequently jammed, misaligned, or failed to lock properly, resulting in delays cascading throughout Amtrak and NJ Transit rail operations. The new Portal North Bridge, scheduled to reach substantial completion by 2026, is being constructed to completely eliminate these issues by replacing the antiquated swing bridge with a high-level, fixed-span structure that no longer needs to open for river traffic. Construction of the new bridge began with extensive site preparation, including the relocation of utility lines, clearing of right-of-way areas, and installation of cofferdams in the river to allow work in dry conditions. The foundation phase focused heavily on deep foundation elements to support the massive structure. Driven steel piles and drilled shafts were installed to reach down through layers of river sediment and into bedrock, ensuring the bridge could carry modern rail traffic loads while withstanding hydraulic and seismic stresses. Each pier footing was constructed within these cofferdams using reinforced concrete forms designed to resist buoyant forces from the surrounding water. One of the central design improvements is the elevation of the new fixed bridge approximately 50 feet above mean high water, which accommodates all standard maritime traffic underneath without requiring movable components. The bridge spans approximately 2 miles in total length, incorporating approach viaducts and embankments that gradually rise to meet the central structure. To construct these approach sections, engineers deployed precast concrete girders supported on reinforced piers, enabling repetitive modular assembly with minimized disruption to existing rail operations. The steel superstructure of the main span was fabricated off-site and delivered in large segments. Each segment was hoisted into place using heavy lift cranes operating from barges and temporary trestles erected in the river. The steel girders were bolted and welded together atop temporary falsework, after which the concrete deck was poured using a stay-in-place formwork system. This method ensured tight construction tolerances and allowed simultaneous work on electrical systems and track installation above. Signal and catenary system integration was a major component running in parallel with structural work. Crews installed new overhead contact system poles and strung high-tension wire throughout the new bridge alignment. Track-laying teams followed closely behind, securing continuous welded rail onto concrete ties using high-precision tamping and alignment equipment. Positive train control systems were incorporated into the new signal infrastructure, bringing the bridge in line with modern safety and automation standards. Amid the complex subterranean infrastructure of New York City, the 2nd Avenue Subway Phase 2 project represents a major expansion of transit capacity along Manhattan's East Side, particularly servicing the underserved East Harlem neighborhood. This phase extends the Q line northward from the current terminus at 96th Street up to 125th Street, adding approximately 1.5 miles of new twin-track tunnel and 3 new stations at 106th Street, 116th Street, and 125th Street. Although full completion is expected later, significant early works, tunneling activities, and utility relocations are on schedule to be finalized by 2026, marking a critical milestone in the overall construction timeline. Initial construction efforts have focused on the relocation and protection of underground utilities, a process that requires precision excavation through layers of densely packed infrastructure, including sewer lines, water mains, gas conduits, electrical cables, and telecommunication systems. To accomplish this safely, crews utilized vacuum excavation methods and non-destructive digging tools, mapping utility alignments and rerouting them to clear paths for future excavation. In some areas, new utility corridors were built entirely to support the tunnel boring operations and future station development. Once the utility work reached sufficient progress, tunneling operations commenced with the deployment of tunnel boring machines that were lowered into deep launch boxes constructed along the alignment. These TBMs are massive cylindrical machines equipped with rotating cutter heads designed to bore through Manhattan schist and other geologic layers. As they advanced, the machines simultaneously installed precast concrete tunnel lining segments, forming the structural shell of the subway tunnels. The twin tubes are built with precise curvature and grade to meet performance standards for modern train speeds and passenger comfort. In parallel with tunneling, deep excavation began for the future station caverns. Each station box, particularly the 125th Street Terminal, is being constructed using a combination of cut and cover methods and sequential excavation techniques where appropriate. For deeper sections, rock blasting and mechanical excavation were employed under controlled conditions, with vibration monitoring in place to protect surrounding buildings and infrastructure. Excavated material is removed using muck conveyors and trucked out via dedicated access shafts. One of the most significant aspects scheduled for substantial completion by 2026 is the structural excavation and primary concrete shell of the 125th Street Station. This includes the reinforced concrete station box, invert slab, and column and beam framework that will support platform levels, mezzanines, and ancillary rooms. The work also encompasses critical elements of vertical circulation infrastructure such as elevator and escalator shafts. Completion of this shell by 2026 will allow fit-out phases such as mechanical, electrical, and plumbing installation to begin immediately thereafter. Throughout the alignment, permanent structural support systems like slurry walls, rock bolts, shotcrete linings, and waterproofing membranes are being installed in stages, often following close behind excavation fronts. Utility infrastructure is being rebuilt to modern standards with upgraded capacity, redundant power feeds, and new stormwater management systems. By 2026, the completion of tunneling, station cavern excavation, and core structural concrete work marks a pivotal transition point in Phase 2 of the 2nd Avenue subway. It sets the stage for the interior outfitting, systems installation, and track work that will follow, ultimately advancing the long-awaited goal of extending high-capacity subway access to communities that have endured generations without it. In the expanse of the Texas Panhandle, the Sanford Dam plays a pivotal role in regional water management and flood control, particularly as it impounds Lake Meredith on the Canadian River. Originally constructed in the early 1960s, the dam was designed as an earth-fill embankment with a concrete spillway, serving the dual purposes of municipal water supply and mitigating downstream flooding. Over time, the infrastructure aged, prompting a phased rehabilitation effort aimed at enhancing safety, structural resilience, and operational efficiency. By 2026, significant structural upgrades and instrumentation installations are scheduled for completion, focusing on both the dam body and the outlet work system. One of the central aspects of the modernization program involves strengthening the earthen embankment, which spans nearly 7,000 feet in length and rises over 100 feet above the original riverbed. Crews began by performing extensive geotechnical investigations, including borehole sampling and soil stability analysis, to identify zones of potential seepage or differential settlement. Based on these findings, filter and drain systems were redesigned. A new chimney filter composed of well-graded sand and gravel was installed internally, sandwiched between impermeable clay cores and the outer embankment shell. This redesign allows any infiltrating water to be safely collected and discharged, significantly reducing the risk of piping failure. The downstream slope was regraded and armored with riprap composed of heavy angular rock to guard against erosion from rainfall and potential overtopping. In conjunction with this, tow drains and relief wells were refurbished or newly constructed to relieve hydrostatic pressure and to provide observable points of seepage monitoring. Construction sequencing was carefully managed to maintain reservoir capacity and dam integrity, with earth-moving equipment operating in staged zones and GPS-controlled graders ensuring design specifications were met. The spillway system, originally cast in reinforced concrete and located near the left abutment, underwent its own set of enhancements. Cracking and scaling on the spillway crest and chute surfaces were repaired using epoxy injection and shotcrete overlay techniques. Expansion joints were replaced with water stops designed to accommodate thermal movement while maintaining water tightness. New aerators were installed within the chute profile to minimize cavitation damage under high flow conditions. The stilling basin at the spillway's toe was also restructured with improved energy dissipation blocks and reinforced apron slabs. Another major element reaching completion by 2026 is the modernization of the outlet works. The original gated conduits and control valves were replaced with stainless steel slide gates operated by hydraulic actuators housed within a new gate chamber structure. This upgrade improves flow regulation, allowing more precise water delivery to downstream users. New access galleries were constructed for maintenance and inspection, and redundant power supply lines were routed to ensure system operability during electrical outages. A comprehensive instrumentation network was added throughout the dam structure and appurtenant works. Vibrating wire piezometers, inclinometers, and settlement plates were embedded at key points to monitor pore pressure, movement, and subsurface changes in real time. These data feeds are linked to a centralized supervisory control and data acquisition system, which supports predictive maintenance and emergency response planning. Rising from the ground in Orchard Park, New York, the new Highmark Stadium is a major construction endeavor aimed at delivering a state-of-the-art home for the Buffalo Bills and redefining the game day experience in Western New York. This open-air stadium replaces the aging original Highmark Stadium and is being built with a focus on durability, fan engagement, and advanced operational systems suitable for the harsh winter climate of the region. By 2026, the structural steel framing, precast concrete bowl, and building envelope are all projected to be complete, marking a major milestone in the stadium's delivery timeline. Construction began with extensive site grading and earthwork to shape the subgrade and install foundational infrastructure. The site preparation phase involved removal of unsuitable soils, installation of stormwater management systems, and placement of engineered fill to ensure proper compaction and drainage. Deep foundations using drilled shafts and large diameter piers were installed to support the stadium's superstructure, particularly beneath the main seating bowl and roof canopy supports. These foundations were embedded into the region's bedrock using high-capacity rebar cages and tremie-poured concrete to deliver structural stability under heavy snow and wind loads. Once the foundation work was finalized, erection of the stadium's structural steel frame commenced. Large steel columns and trusses were fabricated off-site and transported in segments to be assembled using high-capacity crawler cranes and bolted field connections. The steel structure forms the skeletal framework for the seating tiers, premium suites, press boxes, and canopy roof system. Parallel to this, precast concrete risers and seating platforms were installed in a stepped sequence to form the lower and upper bowls. These concrete components are cast with integrated utility conduits and anchorage points for seats, railings, and electrical fixtures. A major feature of the stadium is its asymmetrical canopy design, which is intended to shield the majority of fans from snowfall and wind while leaving the playing field open to the elements in true Buffalo fashion. The canopy is supported by a series of tapered box girders and cantilevered trusses extending outward from the upper bowl's compression ring. Roof decking includes insulated metal panels with integrated snow guards and drainage paths to direct meltwater safely to ground level. Mechanical, electrical, and plumbing systems have been progressing simultaneously with structural work. Central utility corridors were embedded into the lower levels, carrying chilled water, gas, electrical service, and communication cabling. Utility nodes are distributed throughout the concourses and suites to accommodate concession equipment, digital signage, lighting, and ventilation. High-efficiency HVAC units, snow melt systems for walkways, and smart lighting controls are all part of the sustainable design strategy. By 2026, the entire stadium structure, including the concrete bowl and canopy roof, will be completed and fully enclosed. This enables interior fit-out phases to begin, which will involve installation of seats, finishes, digital infrastructure, and audio-visual systems. The building envelope, consisting of curtain wall glazing, insulated metal panels, and high-performance weatherproofing, will be sealed to withstand Western New York's freeze-thaw cycles and high wind events. Beneath the urban fabric of West Baltimore, one of the most significant rail infrastructure upgrades on the Northeast Corridor is unfolding with the Baltimore and Potomac Tunnel Replacement Project. This effort targets the elimination of a critical choke point where trains must slow to under 30 miles per hour to navigate through a pair of antiquated brick-lined tunnels built shortly after the Civil War. These tunnels, suffering from water infiltration, tight curvature, and poor vertical clearances, have long constrained passenger and freight operations. The new tunnel system, named the Frederick Douglass Tunnel, will consist of modern twin bores capable of supporting high-speed electric trains with full electrification, and by 2026, a substantial portion of the tunnel excavation and concrete lining work is expected to be completed. Initial stages of the project involved complex site preparation across multiple urban blocks. Utility relocation was one of the most challenging undertakings, as high-voltage electrical feeders, water mains, sewer lines, and communication ducts had to be rerouted or supported in place while maintaining service to surrounding neighborhoods. Surface access shafts were excavated using slurry wall techniques, allowing for deep vertical entry points that serve as launch and retrieval sites for tunnel boring machines. The TBMs used on this project are customized for soft ground tunneling with pressurized face systems to prevent ground settlement and surface disruption. As the TBMs advance, they simultaneously install precast concrete segment rings to form the tunnel lining. Each segment is bolted and gasketed to ensure watertight integrity. An annular grout is injected to fill the gap between the lining and the surrounding earth. To optimize logistics, a continuous muck removal system conveys excavated material through the tunnel to the surface, where it is processed and hauled away. Tunnel invert slabs and track bed preparation follow closely behind the TBM progress. This includes installation of reinforced concrete floors, embedded conduits for drainage and cabling, and future attachment points for the track slab. High-capacity ventilation ducts, lighting conduits, and emergency egress pathways are also integrated during this phase, allowing for a compact and efficient systems corridor. At ground level, the project includes new approach tracks and interlockings with modern signal systems. Work crews are laying new ballastless track using direct fixation methods, ideal for tunnels where precision alignment and vibration control are critical. Turnouts and crossovers near the portals are supported by precast plinths and coordinated with real-time signal interlock logic for safe switching operations. By 2026, the majority of tunnel excavation, structural lining, and invert construction will be finished, providing a continuous twin-tube shell beneath West Baltimore. Simultaneously, the construction of key ancillary facilities, such as traction power substations, ventilation shafts, and emergency exit buildings, will reach advanced stages of completion. These surface-level components are essential to the tunnel's overall operation and are built to withstand fire, seismic events, and external weather conditions. Towering cranes and steel skeletons have come to define the skyline around Nashville International Airport, where the BNA Vision project is unfolding as a multi-phase transformation of terminal infrastructure, passenger amenities, and operational capacity. This sweeping development plan is designed to accommodate explosive regional growth and rising air travel demand. As part of this ongoing program, by 2026, several major components will reach full completion, including expanded concourses, a new on-airport hotel, and integrated ground transportation facilities, all aimed at redefining the traveler experience while future-proofing the airport's functionality. Central to the effort is the construction of a new terminal lobby and ticketing hall expansion, which involves reconfiguring the central terminal core with additional vertical space, new structural framing, and large-span roof trusses. This lobby incorporates high-performance glazing systems for natural light, post-tensioned concrete slabs for uninterrupted floor plates, and advanced mechanical systems to handle the increased foot traffic. The new hall connects seamlessly to both the south and north concourses, forming a unified passenger circulation loop. One of the largest structural packages nearing completion by 2026 is the satellite concourse expansion. Built with steel framing and deep foundation systems, the expanded concourse adds dozens of new gates equipped with modern boarding bridges, energy-efficient HVAC systems, and wide passenger hold rooms. Each gate is supported by a modular utility backbone that includes data cabling, potable water, and baggage handling extensions. The floor assembly utilizes composite steel decking with concrete topping slabs, designed to support both passenger loads and integrated seating, charging stations, and wayfinding systems. Adjacent to the terminal is the new hotel development, a significant vertical addition to the campus. This high-rise structure is built using reinforced concrete cores and shear walls to provide lateral stability against wind and seismic forces. The hotel, which is on schedule for full interior completion by 2026, is directly connected to the terminal via a covered pedestrian bridge and includes amenities such as conference rooms, restaurants, and observation decks overlooking the airfield. Mechanical plant systems are located on rooftop penthouses, concealed by architectural screening, and are supported by a network of steel beams and slab-on-metal deck construction. On the airside, airfield reconfiguration and apron expansions are underway to support the added gate capacity. This includes new concrete paving slabs poured in large contiguous sections with dowel baskets, expansion joints, and embedded lighting. Jet fuel hydrant systems are integrated beneath the apron surface, supported by trench access points and utility vaults. Stormwater runoff is controlled by a series of trench drains and retention basins designed to meet FAA environmental compliance standards. Ground transportation infrastructure is also being upgraded as part of the BNA Vision, with new roadways, parking garages, and shuttle facilities. These structures are built using precast concrete panels and post-tension beams for fast-track assembly. Intelligent transportation systems are embedded into the structure, with real-time occupancy sensors, automated ticketing systems, and dynamic signage. Stretching across agricultural fields and transportation corridors in California's Central Valley, the Hanford Viaduct is one of the most prominent elevated structures in the state's high-speed rail program. Designed to carry future high-speed trains over highways, irrigation canals, and local roads, this viaduct exemplifies long-span bridge engineering on a linear infrastructure scale. Extending more than 6,000 feet in length, the structure is a major part of the route connecting the cities of Bakersfield and Merced. By 2026, substantial portions of the viaduct's superstructure and supporting piers are scheduled for full completion, marking a key advancement in California's effort to build the nation's first dedicated high-speed rail system. Construction began with foundation work on deep pile supports, essential for distributing loads through the soft valley soils and into more stable substrata. Each pile cap anchors groups of cast-in drilled hole piles, some reaching depths of over 100 feet. These piles were installed using large rotary drilling rigs, followed by steel cage placement and concrete pours using tremie methods to avoid soil intrusion. Reinforced pile caps were then formed and cast to support vertical columns rising in pre-engineered intervals along the structure's path. The viaduct's columns are typically cast in place, reinforced concrete shafts with integrated rebar cages designed to resist bending and shear forces from seismic events. Column heights vary based on topography and the elevation required to clear existing obstacles, such as State Route 198 and other major infrastructure. Formwork systems were employed in a climbing sequence, allowing successive concrete pours to build up each column in increments. Once cured and post-tensioned, these columns were capped with pier tables, forming the intermediate support points for the superstructure. The superstructure itself consists of precast concrete girders installed using balanced cantilever construction techniques. Segments were fabricated at a dedicated casting yard, then transported to the site via specialized haulers. Large capacity cranes and launching gantries were used to lift and position these segments atop pier caps, where they were aligned and post-tensioned together with steel cables. This method minimized on-site curing time and allowed for faster assembly across long spans without requiring extensive scaffolding or temporary shoring in active roadways or sensitive environmental zones. Bridge deck construction followed closely behind girder placement. Deck slabs were cast in place atop the precast segments using slip-form paving machines and high-strength concrete mixers designed for thermal resistance and structural integrity. Expansion joints, shear connectors, and deck drainage features were integrated into the pour sequence. Parapet walls and safety barriers were cast with embedded conduit for future rail electrification and signaling systems. By 2026, the entire structural assembly of the Hanford Viaduct, including all columns, girders, and deck sections, is expected to be completed, enabling future track installation and system outfitting. This milestone signals the transition from heavy civil construction to rail-specific phases such as ballastless track slab installation, overhead contact system erection, and control system integration. Set in the rolling terrain of Fannin County, Texas, the Leonhurst Dam is a key feature in the development of Lake Ralph Hall, a major water supply reservoir under construction to meet the growing demands of the North Texas region. This dam is a crucial component of a broader infrastructure program designed to provide long-term water reliability while incorporating environmental and recreational benefits. The project includes an earthen embankment dam, intake and outlet structures, spillways, and various support facilities. By 2026, the dam embankment, outlet works, and much of the lake basin clearing and impoundment control systems are scheduled for completion, representing the functional establishment of the reservoir. The dam itself is a zoned earthfill embankment, meaning it is constructed using distinct layers of different soil materials, each selected for specific geotechnical properties. The central core is composed of low permeability clay, forming an impermeable barrier to prevent seepage. This core is flanked by progressively more permeable materials, sand, gravel, and rock, that provide both structural support and controlled drainage. These zones are compacted in thin lifts using heavy compaction equipment to achieve the necessary density and bonding between layers. Foundation preparation was one of the earliest and most critical steps in the construction process. It began with stripping of topsoil and removal of organic materials, followed by proof rolling and excavation down to suitable bearing strata. A cut-off trench was excavated beneath the core zone and keyed into bedrock or highly consolidated clay, effectively reducing the risk of underseepage. As an added precaution, grout curtains were drilled along the alignment to seal fractures and enhance subsurface impermeability. As the embankment rose, real-time monitoring was implemented using inclinometers, piezometers, and settlement gauges. These instruments provided engineers with continuous data on pore water pressures, lateral movement, and vertical deformation, allowing timely adjustments to fill placement and moisture conditioning. The upstream slope of the dam was armored with riprap to guard against wave action and erosion once the reservoir reaches operational levels, while the downstream slope was protected with turf reinforcement and slope drains. The outlet work structure, also on track for completion by 2026, consists of a reinforced concrete intake tower, gated conduit, and stilling basin. The intake tower includes multiple inlets at different elevations, allowing selective withdrawal for optimal water quality. Flow from the intake travels through a concrete-lined tunnel beneath the dam, controlled by a series of hydraulically operated gates and valves. At the toe of the dam, flow is discharged into a stilling basin lined with energy dissipation blocks and reinforced slabs to prevent scour and erosion. Spillway construction includes a broad-crested weir and a concrete chute extending down the abutment. The spillway is designed to safely pass the probable maximum flood without overtopping the embankment. It incorporates erosion-resistant lining and aerators to minimize cavitation effects during high-velocity flow events. By 2026, the dam embankment and hydraulic structures will be fully constructed, enabling the initial stages of reservoir impoundment and system commissioning. This milestone signifies the transformation of the site from an active construction zone into a functioning regional water resource, marking a major advancement in North Texas water infrastructure.